Hello everyone, in this lecture I'm going to talk about section 1.3 conditional statements. In order to start this section, we have to first define a new operation, new logical operation. So far we have seen conjunction, disjunction, so this is a new operation which is called conditional operation. The conditional operation is denoted with this symbol. It's a arrow to the right. The preposition P arrow Q, which is read if P then Q, is a proposition that we call it conditional proposition. So a compound proposition that uses a conditional operation is called a conditional proposition. P then Q or if P then Q is a conditional proposition. So before knowing the truth value of this conditional proposition, we are going to define the elements of this proposition. Sometimes we refer conditional propositions as a conditional statement, but you can use any of them. Conditional proposition and a statement are both fine. The first element of a conditional statement is called hypothesis. So if you have P then Q, the proposition P in the left hand side of the statement is called the hypothesis of the conditional statement, and the proposition Q on the right hand side of the conditional operation is called the conclusion. Now that we have defined the elements of a conditional statement, let's see what the truth table of conditional operation is and how it looks like. As you see here, since we have two variables in a conditional proposition, we need to have a truth table with four rows. The values of P and Q can be true, true in the first row, true, false in the second row, false, true in the third row, and in the last row we have false, false. The truth value of the propositional the conditional statement P then Q is true in the first row when both P and Q are true. It is false in the second row when P, which is hypothesis, is true, but Q, which is conclusion, is false. Interestingly, when P is false in the last two rows, the value of conditional statement is still true, which means that if hypothesis is false, no matter what the value of Q is, the conditional statement is true. So in the third row, we have P as false, but Q is true. Therefore, the conditional statement is true. In the last row, we have both hypothesis and conclusion as false, but still we have a true conditional statement. So you need to remember this. In the truth table of a conditional operation, all the rows except the second row in which hypothesis is true and conclusion is false is true. Only in the second row when hypothesis is true and conclusion is false, the value of the conditional statement is false. So let's look at an example. Here's the example. If you mow Mr. Smith's lawn, then he will pay you. The the hypothesis in this proposition is you mow Mr. Smith's lawn. We use P to represent this sentence, this proposition. And then the conclusion is represented by Q. So what is Q? Q is he will pay you. Mr. Smith pays you. So there are two different values for P, two different values for Q. If P is true, which means that you mow Mr. Smith's lawn, then then there are possibilities for Q. He pays you or he doesn't pay you. Also, if don't mow Mr. Smith's lawn, again, Q has two different possibilities. Either Mr. Smith pays you or he doesn't. Let's look at all the four possibilities and see what the value of conditional statement and definition of conditional operation. In the first case, when P and Q are both true, which means you mow Mr. Smith's lawn and he pays you, obviously the value of P and Q should be true, right? You mow his lawn, he pays you. In the second case, when you mow his lawn but he doesn't pay you, not true. This should be false. The conditional statement in this case should be false because the contract is broken. The contract was this: if you mow, then he has to pay you. But so in the second case, the contract is broken, and something is wrong. So the conditional statement, the conditional proposition, is false. Let's look at the third case. The third case in which you don't mow his lawn and he pays you doesn't contradict the contract that you had with Mr. Smith, because you didn't mow, but he wanted to pay you anyway. So there's nothing wrong with that. He's generous. In the last case, when P and Q are both false, so you don't mow his lawn and he doesn't pay you. Again, no one uh, violated the contract. You don't mow his lawn and he's not paying you. Everything is false. So as long as the contract is uh, not violated, the value of P then Q, or if P then Q, which is the conditional statement, is true. Only in the second case, when you mow but he doesn't pay, the contract is broken. Therefore, the conditional statement is false. There are different ways to express a conditional statement in English. So let's consider the same example. The proposition P is you mow Mr. Smith's lawn, and Q is Mr. Smith will pay you. So there are different ways to express this the proposition P then Q in English. The first one is very simple: if P comma then Q, which means if you mow Mr. Smith's lawn, then he will pay you. The second one is the same as the first one, but you can simply uh, remove the word if P comma Q. If you mow Mr. Smith's lawn, comma, he will pay you. The third one, we first mentioned Mr. Smith will pay you if you mow his lawn. Again, same proposition, different expression. The fourth one is P implies Q. Mowing Mr. Smith's lawn implies that he will pay you. Uh, the fifth one is using the word only if between P and Q. You will mow Mr. Smith's lawn only if he pays you. The sixth one is P is sufficient for Q, which means P is a sufficient condition for Q. Mowing Mr. Smith's lawn is sufficient for him to pay you. The last one is Q is necessary for P. If P then Q, then we can say Q is a necessary condition for P, which means that Mr. Smith paying you is necessary for you to mow his lawn. The converse of a conditional proposition like P then Q is defined as Q then P. So remember, when we say find the converse of a conditional proposition, we mean you need to swap the place of the place of hypothesis and conclusion. So instead of saying P then Q, you say Q then P. The contrapositive of a uh, conditional statement is like P then Q is not Q then not P. So if we have hypothesis and conclusion, we negate them at the same time. So the negation, the contrapositive of P then Q becomes not Q, then not P. Another form of a conditional proposition is its inverse. The inverse of P then Q is not P then not Q. So we basically negate both the hypothesis and the conclusion. So negation, the inverse of P then Q becomes not P then not Q. Here in this table, you can see the converse, contrapositive, and inverse of a uh, conditional proposition. Here's the example. If it is rainy today, then the game will be canceled. This is the original proposition. Now let's see how the converse of this proposition looks like. If the game is canceled, it is rainy today. So we basically swap the hypothesis and conclusion. The contrapositive of that statement becomes if the game is not canceled, then it is not rainy today. This is the contrapositive of the original proposition. How about the inverse? The inverse of the proposition is if it is not rainy today, then the game will not be canceled. So we simply negate both the hypothesis and the conclusion. Later, we will see that the inverse of a proposition and the converse of the proposition have equivalent truth values. So the inverse of a proposition is equivalent to the converse of the proposition, and the contrapositive of a proposition is logically equivalent to the original proposition. So in this table, the first one and the third one are equivalent, and the second one and the fourth one are equivalent. But the first and last rows are not equivalent. The first and last rows are not equivalent. The second and last rows are not equivalent. The third and last rows are not equivalent. We will talk about the logical equivalence of these forms later. Now let's talk about biconditional operation. If P and Q are two propositions, then the proposition P, if and only if Q, is expressed with the biconditional operation, and it is denoted by this symbol. It's a two-way arrow to the left and arrow to the right. So this is another logical operation that we call it biconditional operation, and we read it as PQ, or sometimes we use the term IFF, which is an abbreviation for the expression if and only if. Therefore, P if and only if Q can be written as P space IFF space Q, which means P if and only if Q, which means the biconditional of P and Q. So let's see how the truth table of the biconditional operation looks like. Again, as you know, we have two variables, therefore we need four different rows. P and Q can be a true in the first row, true in the second row, false true in the third row, and false in the last row. In the first and last row, in which both P and Q have the same truth values, the value of biconditional operation is true. In the third row, in which P and Q have opposite truth values, the truth value of the biconditional operation is false. So if you remember, This is exactly the negation of XOR operation. In the XOR operation, we had the opposite situation. In the first and last row, we had false values. In the second and third row, we have true values. So we can consider conditional operation as the negation of exclusive OR operation.